In this video, we're going to cover all the organic synthetic routes in A-Level Chemistry, looking at all of the different functional group conversions, and then how we can create a synthetic route from going from one functional group to another via multiple different conversions. A synthetic route means making one compound from a different compound. Typically, this will involve multiple steps, going through multiple different functional groups to get to your target molecule from your given starting material. Chemists will try to design synthetic routes which use non-hazardous starting materials and which aren't wasteful. This means the synthetic route will have high atom economies and high percentage yields at each part of the process. This will avoid having too much waste if multiple different steps are used to get from the starting material to the target molecule. This diagram here shows all the different synthetic routes you need to be aware of for A-Level Chemistry. For each of these conversions, for example, alkane to halogenoalkane or ketone to hydroxynitrile, you have to be able to give the reagents and conditions and, where appropriate, draw a mechanism. We're going to look at each of these different conversions in turn, and then we'll look at how we can combine several of these in a series of steps to get from one molecule to another molecule. For each synthetic route, we'll look at the functional group we're starting off with and what our target functional group is, the name of the mechanism involved, an example equation. You could be asked to write an equation for any given starting material, and what reagents and conditions are involved in that conversion. We'll also look at an example mechanism where there is a mechanism for that particular conversion. The first conversion we'll look at is going from an alkane to a halogenoalkane. This is a free radical substitution mechanism. And an example equation shows an alkane molecule reacting with a molecule of the halogen you wish to use to do the conversion, using UV light as a catalyst, producing your halogenoalkane and a molecule of, in this case, HCl, but if you're using a bromine halogen, then you'd form HBr. For example, whatever the halogen you would use, you'd form H and that halogen. The reagents are your halogen, which will be in the form X2, and using UV light as a catalyst. Whilst there isn't a curly arrow mechanism for this process, you do need to be aware of the initiation, propagation, and termination steps. This is the overall equation we looked at a moment ago. The alkane reacting with the halogen in the presence of UV light to make a halogenoalkane and hydrochloric acid. The first step is initiation, to break apart the chlorine into two chlorine radicals. The first propagation step involves the chlorine taking hydrogen off the alkane, leaving an alkyl radical and HCl. The second propagation step is the alkyl radical reacting with a molecule of our halogen to produce our halogenoalkane and to regenerate the radical we used in the first step. And the termination step could be two different alkyl radicals coming together to make a different alkane. In this case, two ethyl radicals reacting together to make butane. For the conversion of a halogenoalkane into a primary amine, this uses the nucleophilic substitution mechanism. An example equation shows our halogenoalkane reacting with two equivalents of ammonia to produce our amine and 1 molecule of NH4Cl. The reagents for this reaction is using excess ammonia and heat. Excess ammonia ensures that we'll produce the amine, as it should prevent too much of the amine reacting with our halogenoalkane starting material, but some side reactions are still possible during this process. An example mechanism would start with our halogenoalkane and our ammonia. The lone pair in the ammonia will attack the carbon. This will be slightly positive because it's next to the chlorine, which is slightly negative. The second arrow will be the breaking of the carbon-chlorine bond, with the arrow going to the chlorine. This will produce the following intermediate structure, noting the nitrogen has got a positive charge, as it now has one more bond than it started off with. The final step of the mechanism being the loss of a hydrogen, with the arrow going from the NH bond to the nitrogen. And this will produce our desired amine product. The conversion of a primary amine to a secondary, tertiary or quaternary amine uses the nucleophilic substitution mechanism. And an example equation would show the, in this case, primary amine reacting with a molecule of halogenoalkane to produce a secondary amine, as we've now got two CH3 groups attached to the amine, and a molecule of HBr. The reagents and conditions for this reaction would be using excess halogenoalkane, so there's multiple halogenoalkanes available for the amine to react with, and heating this reaction up. An example mechanism would start with the halogenoalkane and the primary amine. The reaction will start with the lone pair on the nitrogen attacking the carbon, and the carbon-bromine bond being broken, so the arrow going from the bond to the bromine. That will give us the following intermediate structure. So we've now added the methyl group onto the other side of the molecule, and our nitrogen will have a positive charge. As before, the NH bond will be broken, with the arrow going from the NH bond to the nitrogen, producing our secondary amine product. You can see how our secondary amine could then redo the reaction we've looked at, so the lone pair on the nitrogen attacking the carbon, displacing the bromine, and that's how we could then form a tertiary or a quaternary ammonium salt. For the conversion of a halogenoalkane into a nitrile, it uses a nucleophilic substitution mechanism. An example equation would show the halogenoalkane reacting with a molecule of potassium cyanide to form a nitrile and a molecule of potassium chloride. The reagents and conditions for this reaction is potassium cyanide in an ethanol solvent, and it would need to be refluxed. The mechanism would involve a molecule of halogenoalkane and the nitrile ion. The lone pair on the carbon would attack the carbon on the halogenoalkane, with the carbon-halogen bond being broken, with the arrow going from the middle of the bond to the chlorine. And this would produce the target nitrile molecule. For the conversion of a nitrile to a primary amine, this would be a reduction mechanism. The equation would be your nitrile with 4 equivalents of the reducing agent to produce your target amine. The reagents and conditions for this reaction is lithium aluminium hydride in a dry ether solvent in the first step, followed separately by dilute acid. These steps must be clearly labelled 1 and 2. Alternatively, you could use hydrogen gas with a nickel or platinum catalyst at high temperatures or pressures. This mechanism is typically used to produce an amine over the production of an amine from a halogenoalkane, as it only produces a single primary amine product without any possibilities of sides reactions taking place. There isn't a mechanism you need to learn for this reaction. For the conversion of a halogenoalkane into an alkene, this is the elimination mechanism. An example equation would show our halogenoalkane reacting with sodium hydroxide to produce our alkene, our halogen salt, and water. The reagents and conditions for this reaction is using sodium hydroxide or potassium hydroxide, warming the reaction, and using an ethanol solvent. An example mechanism would have our halogenoalkane and our hydroxide ion. The lone pair on the oxygen attacks a hydrogen on the carbon adjacent to our halogenoalkane. The carbon-hydrogen bond breaks, this will form a double bond, and the carbon-halogen bond will then be broken. This will produce our desired alkene product. For the conversion of a halogenoalkane into an alcohol, this is the nucleophilic substitution mechanism. An example equation shows our halogenoalkane reacting with sodium hydroxide to produce the alcohol and a sodium halogen salt, in this case sodium bromide. Our reagents and conditions would be the sodium hydroxide or potassium hydroxide in reflux conditions in an aqueous solvent. The mechanism starts off with our halogenoalkane and our hydroxide ion. The lone pair on the oxygen attacks the carbon. The carbon-bromine bond breaks, giving us our desired product of an alcohol. For the conversion of an alkene into a halogenoalkane, this would be the electrophilic addition mechanism. An example equation would show the alkene reacting with a molecule such as HBr to produce our halogenoalkane. The reagents and conditions are our electrophile, for example HBr, or you could have any halogen in the form HX. You could also have a dihalogen, i.e. Br2, and any halogen would work in this way as well. The reaction will be carried out at room temperature. The mechanism starts out with the alkene and our electrophile. The first step involves a double bond attacking the hydrogen, so the arrow starting in the middle of the double bond and coming to the hydrogen, then the hydrogen-bromine bond being broken, so the arrow going from the middle of the bond to the bromine. In this reaction, you have a choice of products, depending on what the most stable carbocation intermediate is in the reaction. That will depend on how many carbon groups are attached to the carbon which could have the positive ion, the carbocation. If you're unsure how to determine which product could be produced, revisit the alkenes topic for revision. The final step in the mechanism is the lone pair on the halogen attacking the positive carbon. To produce the desired halogenoalkane product. For the conversion of an alkene into a polyalkene, this is a polymerization reaction. An example equation might show your alkene monomer forming your polymer repeating unit. Note the brackets going through the trailing bonds and the N to indicate the number of repeating units that you have. The conditions will depend on the type of monomer being used. Some require high pressures and temperatures and catalysts to be used, but the conditions will vary based on your starting monomer and the type of reaction you're trying to do. There is no set mechanism you need to learn for this process. For the conversion of an alkene into an alcohol, this is an electrophilic addition mechanism, sometimes also referred to as a hydration reaction. An example equation would show a molecule of ethene reacting with water with a phosphoric acid catalyst to produce your alcohol. The reagents and conditions for this reaction is using phosphoric acid and steam at 300 degrees and 60 atmospheres of pressure. You can also use a combination of sulfuric acid and water as well. An example mechanism would show your alkene and a H+, the H+ coming from the phosphoric acid catalyst. The first step would be the double bond attacking the H+ ion, producing a carbocation intermediate, and like the other electrophilic addition reaction we looked at, the most stable carbocation intermediate would form. We also then have a molecule of water. The lone pair on the water will then attack the positive carbon atom, which will produce the following intermediate structure. So an OH2 molecule attached to the carbon with the oxygen having a positive charge. One of the oxygen-hydrogen bonds will then be broken, so the arrow going from the middle of the bond to the oxygen, producing our alcohol molecule. For the conversion of an alcohol into an alkene, this would be an elimination mechanism, sometimes also called a dehydration process. An example equation would show your alcohol with a sulfuric acid catalyst, producing your alkene and a molecule of water. The reagents and conditions for this reaction is just using concentrated sulfuric acid. An example mechanism would show your alcohol and a H+, the H+ coming from the sulfuric acid catalyst. The first step of the mechanism would involve the lone pair on the oxygen attacking the H+, forming the following intermediate structure with an OH2+ attached to the carbon, with a positive charge being on the oxygen. This will then leave the molecule, so the carbon-oxygen bond being broken, with the curly arrow going from the middle of the bond to the oxygen atom. Which will produce the following intermediate structure. Note that it's a carbocation, so there's a positive charge on the carbon. And the final step being one of the carbon-hydrogen bonds being broken, and this will then form the double bond. So the CH bond will have the arrow in the middle of that, going to the middle of the CC single bond. This will then produce the alkene molecule. For the conversion of an alcohol into an aldehyde, this is an oxidation mechanism. An example equation would show the alcohol reacting with one equivalent of oxidizing agent to produce the aldehyde and a molecule of water. The reagents and conditions would obviously be a primary alcohol starting material, acidified potassium dichromate, and distillation conditions. There is no mechanism you need to learn for this process. For the conversion of an alcohol into a ketone, this is also an oxidation process. An example equation for this process would show our alcohol reacting with one equivalent of oxidizing agent to produce our ketone and water. The reagents and conditions would be a secondary alcohol with acidified potassium dichromate being refluxed. Again, there is no mechanism you need to learn for this reaction. For the conversion of an alcohol into a carboxylic acid, this is once again an oxidation process. An example equation would show an alcohol reacting with two equivalents of oxidizing agent to produce a carboxylic acid and water. The reagents and conditions would be a primary alcohol, acidified potassium dichromate, and the reaction done in reflux. There is no mechanism you need to learn for this reaction. For the conversion of an aldehyde into a carboxylic acid, this again would be an oxidation process. An example equation would show the aldehyde reacting with one equivalent of oxidizing agent to produce a carboxylic acid. The reagents and conditions would be acidified potassium dichromate and reflux would be needed. For the conversion of an aldehyde or ketone to a hydroxynitrile, this would be a nucleophilic addition mechanism. An example equation would show, in this case, an aldehyde reacting with potassium nitrile to form our hydroxynitrile product. The reagents and conditions would be acidified potassium cyanide or hydrogen cyanide with the reaction done at room temperature. An example mechanism would show our aldehyde or ketone and our nitrile ion. The lone pair on the carbon would attack the other carbon, with the carbon-oxygen double bond being broken, the arrow going from the middle of that double bond up to the oxygen. Our intermediate structure now shows the oxygen with a single bond to the carbon and a negative charge, and a hydrogen ion, which comes from the acidified reagents we are using. The lone pair on the oxygen will then attack the hydrogen ion, giving us our desired hydroxynitrile product. For the conversion of an aldehyde or ketone into an alcohol, this would be a nucleophilic addition mechanism, but it's also an example of a reduction process. The aldehyde or ketone would react with two equivalents of the reducing agent to produce the desired alcohol. The reagents and conditions would be sodium borohydride and water. An example mechanism would show the aldehyde or ketone and a H- ion, the lone pair on the H- ion will attack the carbon-oxygen double bond will be broken, so the curly arrow will go from the middle of that double bond up to the oxygen. The intermediate structure will have an oxygen with a negative charge and a single bond to the carbon. The hydrogen ion will come from the water. The lone pair on the oxygen will attack the hydrogen ion. Giving us the desired alcohol product. For the conversion of an alcohol into an ester, this would be an esterification process. An example equation would be an alcohol reacting with a carboxylic acid to produce an ester and water. The reagents and conditions would be a carboxylic acid, concentrated sulfuric acid under reflux. This would also be the same conversion for a carboxylic acid producing an ester, apart from a carboxylic acid being a reagent. In that case, the alcohol would be. There is no mechanism you need to learn for this process. For the conversion of an ester back into an alcohol in carboxylic acid, this is a hydrolysis reaction. And an example equation would show an ester reacting with water to produce a carboxylic acid and an alcohol. The conditions for this reaction would be dilute sulfuric acid or dilute sodium hydroxide, depending on whether you're wanting to do acid or base hydrolysis, water, and reflux conditions. For the conversion of an acyl chloride or an acid anhydride into a carboxylic acid, this would be a nucleophilic addition-elimination mechanism. Example equations are given for both the acyl chloride and the acid anhydride. So the acyl chloride would react with water to produce the carboxylic acid and hydrochloric acid. The acid anhydride would react with water to produce two equivalents of the carboxylic acid. The reagents and conditions would be water at room temperature. For nucleophilic addition-elimination reactions, you need to know the mechanism if an acyl chloride is used, but not if an acid anhydride is used. So the following four examples will just look at acyl chlorides. So you'd have your acyl chloride, and in this case, water. The lone pair on the oxygen would attack the carbon. The carbon-oxygen double bond would be broken, with the curly arrow going from the middle of that double bond up to the oxygen. The intermediate structure would have now a carbon-oxygen single bond. Our OH2 group which is joined would now have a positive charge on the oxygen. These curly arrows may be shown in a single step or two separate steps. So for example, this is the first step and this is the second step. The lone pair on the oxygen will reform the double bond and the chlorine will be eliminated. One of the hydrogens on the oxygen will drop off, so the oxygen-hydrogen bond will be broken, with the curly arrow going to the oxygen. This will give us our carboxylic acid product. For the conversion of an acyl chloride or an acid anhydride to an ester, This would be a nucleophilic addition elimination mechanism. Example equations show an acyl chloride reacting with an alcohol to produce an ester and hydrochloric acid, or an acid anhydride reacting with an alcohol to produce an ester and a carboxylic acid. The reagents and conditions would be an alcohol at room temperature. A mechanism would show an acyl chloride and an alcohol. The lone pair on the oxygen will attack the carbon, and the carbon-oxygen double bond will be broken. The intermediate structure shows an oxygen with a negative charge and now a single bond to the carbon, and a positive charge on the oxygen which attacked the carbon in the first step. The lone pair on the oxygen will reform the double bond, eliminating the chlorine, and the hydrogen from the OH group on the alcohol will drop off with the arrow going from the bond to the oxygen. This will give your desired ester product. For the conversion of an acyl chloride or an acid anhydride to an amide, this will be a nucleophilic addition elimination mechanism. An example equation would show an acyl chloride reacting with ammonia to produce the amide and hydrochloric acid, or the acid anhydride reacting with ammonia to produce the amide and a carboxylic acid. The reagents and conditions would be ammonia at room temperature. The mechanism will show the acyl chloride and a molecule of ammonia. The lone pair on the ammonia will attack the carbon, and the carbon-oxygen double bond will be broken. This will give an intermediate structure with the oxygen with a negative charge and the nitrogen with a positive charge. The lone pair on the oxygen will reform the double bond, eliminating the chlorine, and one of the hydrogen-nitrogen bonds will be broken with the electrons going to the nitrogen. This will form the desired amide product. For the conversion of an acyl chloride or acid anhydride into an N-substituted amide, this will be a nucleophilic addition elimination mechanism. An example equation would show the acyl chloride reacting with a primary amine to form an N-substituted amide and hydrochloric acid, or an acid anhydride reacting with a primary amine to produce an N-substituted amide and a carboxylic acid. The reagents and conditions would be an amine at room temperature. An example mechanism would show an amine and the acyl chloride. The lone pair on the nitrogen will attack the carbon, breaking the carbon-oxygen double bond. Forming an intermediate structure with a negative charge on the oxygen and a positive charge on the nitrogen. The lone pair on the oxygen will reform the double bond, eliminating the chlorine, and one of the NH bonds will be broken with the electrons going to the nitrogen. This will form the desired product of the N-substituted amide. For the conversion of benzene into nitrobenzene, this is an electrophilic substitution reaction, sometimes also called a nitration reaction. The equation for the conversion would be benzene, C6H6, reacting with nitric acid and a sulfuric acid catalyst to produce nitrobenzene and water. You also have to be able to show how the reactive intermediate, NO2+, is formed, which the second equation shows. Your nitric acid reacting with your sulfuric acid to produce your nitro ion. The reagents and conditions for this reaction would be nitric acid, sulfuric acid, and a temperature of below 55 degrees if you want mono substitution. Above 55 degrees, you'll have multiple substitutions taking place. An example mechanism would show the benzene molecule and the nitro NO2+ ion. The first step of the mechanism is the benzene ring attacking the nitro ion. The following intermediate structure will be formed. The carbon-hydrogen bond will be broken, with the arrow going from the carbon-hydrogen bond back into the benzene ring, producing the nitrobenzene product. For the conversion of nitrobenzene into phenylamine, this will be a reduction mechanism. The equation would show nitrobenzene reacting with 6 equivalents of the reducing agent to produce phenylamine and 2 molecules of water. The reagents and conditions for this reaction would be tin with concentrated hydrochloric acid under reflux in the first step, and in a separate step, sodium hydroxide. There is no mechanism you need to learn for this reaction. For the conversion of benzene into a phenyl ketone, this is an electrophilic substitution reaction, also known as an acylation reaction. The equation shows a molecule of benzene reacting with a molecule of acyl chloride with an aluminium chloride catalyst to produce our phenyl ketone and hydrochloric acid. You also have to be able to write an equation to show how the reactive intermediate is formed, in this case the acyl chloride reacting with the aluminium chloride to form our reactive intermediate and an aluminium chloride ion. The reagents and conditions for this reaction is an acyl chloride, our aluminium chloride, under reflux in a non-aqueous solvent. An example mechanism would show the benzene with the reactive intermediate. The benzene ring will attack the positive carbon ion. We'll then have the following intermediate structure, with the carbon-hydrogen bond being broken and the electrons going back into the benzene ring to form our desired phenyl ketone product. We're now going to look at some example conversions of how we would get from one molecule to a different molecule. In this case, we're being asked to go from propane into aminobutane. In this case, it would be 1-aminobutane, as the amino group is on carbon number 1. In order to do this, we'd have to consider the reaction map we looked at the start of the video. We have to be able to get from one functional group to a different functional group. In this case, from an alkane into a primary amine. The route we would take is an alkane into a halogenoalkane, then to a nitrile, then to a primary amine. We notice this particular route as when we go via a nitrile, we add a carbon to the chain. We went from propane to 1-aminobutane. Therefore, we've added a carbon, going from 3 to 4. Therefore, the reaction must proceed via a nitrile rather than just from an alkane to a halogenoalkane to an amine. Now we know the route the reaction is going to take, we can write out all of the steps involved. The first step would involve the conversion of the alkane into a halogenoalkane, so reacting it with a halogen under UV light. The second step would involve the changing of the halogenoalkane into a nitrile by reacting the molecule with potassium cyanide. And the final step of reacting the nitrile with 4 equivalents of the reducing agent to produce the target amine. The conditions and reagents for this reaction being lithium aluminium hydride in dry ether in the first step, and in the second step using dilute acid. In this example, we need to convert benzene into phenylamine. The first step of this being the conversion of benzene into nitrobenzene by reacting it with nitric acid and sulfuric acid. We would have to include the equation to show how the reactive intermediate was produced. The second step being the reaction of the nitrobenzene with 6 equivalents of reducing agent to produce our phenylamine and water. Which would require tin, concentrated hydrochloric acid under reflux in the first step, and sodium hydroxide in a second step. Our final conversion is taking propane and producing propyl propanoate. Once again, we'd have to look at the reaction map to figure out where we're going to go from our starting material to our desired product. So from an alkane to an ester. For this conversion, we'd need to produce 2 separate molecules to react together. So we're going to have to change our alkane into both an alcohol and a carboxylic acid, so we can react both the alcohol and carboxylic acid together to produce an ester. Overall, this is the route we're going to have to take. An alkane into a halogenoalkane, into an alcohol, then take some of the alcohol and convert that to a carboxylic acid, so we can react the alcohol and carboxylic acid together to produce an ester. We wouldn't go from an alkane to a halogenoalkane to an alkene to an alcohol, as this would involve an additional step. And at the start of the video, we talked about how chemists want to do this process with as little waste as possible. Therefore, we should always take the shortest number of steps as possible. So the first step is to produce our halogenoalkane from our alkane, which will involve reacting the alkane with chlorine under UV light to produce the alkane and hydrochloric acid. The second step is the conversion of the halogenoalkane into an alcohol, so reacting the halogenoalkane with sodium hydroxide under aqueous conditions. We then need to convert some of that alcohol into a carboxylic acid, so we would take a sample of that alcohol and react it with 2 equivalents of oxidizing agent to produce our carboxylic acid and water, our oxidizing agent being acidified potassium dichromate. And finally, we'll then react the alcohol and the carboxylic acid together with the sulfuric acid catalyst to produce our ester and water.